Hello, we are Group 9C. My name is Nur Damia binti Ahmad Shaudin, matric number 2511522158.
Hello, my name is Nida Badri Abdul Hamid Joda, matric number 2511502999-1.
And my name is Rawda Zibair Abdul Majid Zibair. My matric number is 2511501711-1. And today we are going to talk about how ultra-low concentration
of neurodegenerative biomarkers
measured for Alzheimer's and ALS.
Alzheimer's disease and ALS are neurodegenerative disorders that cause neuron loss and abnormal protein buildup. They release biomarkers such as amyloid beta tau and neurofilament light chain into blood and cerebrospinal fluid. Since these biomarkers exist at very low levels, ultrasensitive technologies are needed for early detection, diagnosis, and disease monitoring. Despite their importance in early diagnosis, neurodegenerative biomarkers face several challenges. They are present in very low concentration, especially in blood, making detection difficult. Blood also contains many proteins that may interfere with accurate measurement. Although cerebrospinal fluid testing is more sensitive, it requires an invasive lumbar puncture. Another challenge is the lack of standardization between laboratories and testing methods. In addition, some biomarkers are not disease-specific and may be elevated in different neurodegenerative disorders. This limitation can affect diagnosis, patient monitoring, and treatment evaluation. The main objective of this work are to identify key biomarkers for Alzheimer's disease and ALS, including amyloid beta tau proteins, neurofilament light chain, and TDP43. It also reviews ultrasensitive detection technologies such as SIMWA, SMC, IMR, and mass spectrometry, and compares their clinical applications in blood and CSF for early diagnosis and disease monitoring.
The research flow begins with identifying the problem, which is the difficulty in detecting neurodegenerative biomarkers at very low concentrations. Then, a literature review is conducted to understand the relationship between biomarkers and diseases such as Alzheimer's and ALS. Next, the irrelevant biomarkers and detection technologies are identified. After that, the advantages and limitations of each detection method are compared. The results are then analyzed to determine the effectiveness of these technologies in early diagnosis and disease monitoring. Lastly, conclusions and future recommendations are provided based on the findings. Next, I will explain the methodology used in this research. This research is mainly based on a literature review and technology analysis. First, information is collected from scientific journals, research papers, and reliable sources related to Alzheimer's disease, ALS, and neurodegenerative biomarkers. After that, important biomarkers such as neurofilament light chain, NFL, phosphorylated tau, amyloid beta, and GFAP are identified and studied. Next, different ultrasensitive detection technologies including single molecule array, digital ELISA, and mass spectrometry are analyzed to understand how they measure very low biomarker concentrations. Finally, the performance of these methods is evaluated based on their sensitivity, accuracy, detection ability, and potential application in the medical field. Moving on to the advantages and disadvantages of ultra-sensitive biomarker detection methods. One of the main advantages is that these technologies can detect biomarkers at extremely low concentration, allowing earlier diagnosis of neurodegenerative diseases. They also provide more accurate monitoring of disease progression and can use less invasive samples such as blood instead of depending only on cerebrospinal fluid. However, there are also some limitations. These methods require expensive equipment and highly trained professionals to operate. The data analysis can be complex, and some technologies are still not widely available in healthcare facilities. Therefore, although ultra-sensitive detection methods have great potential, improvements in cost, accessibility, and standardization are still needed before they can be widely implemented.
The target output of ultra-sensitive biomarker measurement technology is used for detecting neurodegenerative diseases. These technologies aim to accurately detect and quantify disease-related biomarkers at extremely low concentrations. So the key biomarkers is one, Alzheimer's diseases, which is contained 3 points with amyloid beta proteins, tau proteins, and neurofilament light chain. Second, amyotrophy lateral sclerosis, which is one neurofilament light chain, phosphorylated neurofilament heavy chain, and TDP43 protein. So for the effect on human and medical sector, first of all, gonna talk about human. So the positive effect for human is one, early diagnosis biomarkers can be detected years before clinical symptoms appear. Second of all, improved disease monitoring, disease progression can be tracked more accurately. And third, reduced need for invasive produces blood-based biomarker testing may reduce dependence on lumbar. And for the challenges, we have false positive or false negative results may cause anxiety or delay treatment. And for the medical sector, first, enhance clinical diagnosis and advancement of precision medicine. And third, accelerate drug development and reduce healthcare burden. So for the conclusion, ultra-sensitive measurement technologies have transformed the detection of neurodegenerative biomarkers associated with the Alzheimer's disease and ALS.
By enabling the detection of biomolecules at extremely low concentrations, these methods provide opportunities for earlier diagnosis, more accurate disease monitoring, and improved therapeutic decision-making.
As the biomarker research continues to advance, such technologies are becoming increasingly important for both clinical practice, and biomedical research.
So last but not least, the future recommendations. First, develop affordable point-of-care devices, create portable and cost-effective biosensors for routine clinical screening. Second, integrate artificial intelligence, use AI and machine learning to analyze complex biomarker data sets and improve diagnostic accuracy. Third, promote blood-based testing, expand the use of minimal invasive blood biomarkers. Fourth, establish global standardization, harmonize sample collection, processing, and analytical protocols across laboratories. And fifth, expand multi-biomarkers panels, combine multiple biomarkers rather than relying on a single marker to improve sensitivity and specificity.
I just had to let you know you're